Hello, it's Paul Beckwith back, continuing my discussion on Arctic sea ice and what's happening with this year's melt and what we can expect in the future. So, in the last video, I was talking about the air temperature in the Arctic, and I want to remind people that if you Google Arctic sea ice graphs and you go here, I'm looking at Zack Labe's Arctic sea ice figures at the moment. Okay, so this is the air temperature. Now, this is the zone that we're talking about here. Okay, this is the daily air temperature. And this is north of 80 degrees. Okay, 80 degrees north. That's the 80-degree latitude line. So north of that. And we're getting the air temperature daily. And what we can see is in the winter, we get an awful lot. This is the average from 1958 to 2002, the white line. And this is the variation from year to year, and you can see a lot of fluctuation in the winter here. This goes into the summer, this is the winter here. And the reason that happens, and we're getting, so most of the warming that we're seeing here is in the winter. Okay, and we'll also see the same thing here. You know, we'll see what happens this year. The reason is that the ice in the Arctic acts as a buffer. It takes a lot of energy to melt the ice. So here the energy is going into melting the ice, not changing the air temperature. When that ice, when the Arctic sea ice is gone, there will be a large rise, first of all, in this temperature. So this baseline will move right up. It'll probably continue something like this. Okay, and there'll be tremendous fluctuation as well. There'll be no, there'll be, it looks like the fluctuation as we have a rapidly climbing slope here. It looks like the fluctuation is decreased. There'll still be some fluctuation here, but it's going to be very, very high here. So this is going to, curve is going to come up here. It's going to be very, very high here. And imagine how that will affect the jet streams and growing crops and extreme weather events and heat waves, etc. in the northern hemisphere. We're all going to be buckling our seat belts, and there'll be lots of panic in the public and also scrambling of politicians to say, oh, we never knew this was going to happen. Nobody warned us or told us about that. So you can come back to these videos and say, what are you guys, crazy? Okay, so this is something called freezing degree days. Okay, so let's say the average temperature is minus 5 degrees Celsius for a day in the Arctic. Okay, that's 3.2 degrees Celsius colder than this. So you'd multiply, that would be for a day, you'd have minus 3.2 degrees Celsius day. Now, if you sum that up for each day, then you get this idea of the freezing degree days. So the more you have, the more the ice can form. And it's cumulative, so we're not seeing that in the summer. We're at the freezing point, so this number doesn't change really. And then it starts getting colder. This is the sea ice minimum, it's September, and then it starts getting colder, and we have days that are below freezing. The ice is reforming, so this number accumulates up here. And what we see is, so here's 2017. This is 2016 to 2017. And this is 2017 to 2018 rather, and then 2015 to 2016 was here. So the freezing degree days is nowhere near what it used to be. When it was this cold in the Arctic in the winter, things would freeze up, but now the freeze up is much less, and I showed you the spatial changes of that in the previous videos. The high Arctic, above 80 degrees north, freezing. This is the anomaly in freezing degree days. So here we are you know, 2017 to 2018. Okay, so we're accumulating these, you know, again, the minimum of the ice is September 15th, and then these things start accumulating, and this is the anomaly. They're not accumulating as fast as they used to. So this is 2016, 2017, even worse than this year, 2017, 2018, and there's 2015 to 2016. So the trend is to continue to have smaller and smaller freezing, fewer and fewer freezing degree days, and less ice forming in the winter. And then in the thawing degree days, it's the opposite. It's the temperatures above zero, and what you can see is, you know, the melt really takes off. You know, this is the end of May, beginning of June. So late May, June, you really start getting the warming above zero, above freezing temperatures. Freezing is minus 1.8 for the sea ice. And you start getting a rise here. Now, nothing like the rise, the average in 58 to 2002. Okay. Okay, so what you see here is these 2017, this is 2018 where we are now, 2017, and so the thawing degree days, we're sitting here. Now, accumulated 2 meters, high Arctic, the average was higher here. Higher thawing, more thawing degree days accumulated versus now. I'm a bit puzzled by that. I'll have to think about that. Okay, Arctic temperatures. Okay, so here we are with Arctic temperatures. The mean is the dashed line. Okay, the dashed line is a 1981 to 2010 baseline. Okay, and what we can see is these are different data sets, European, Japanese, American ones, and what you can see is, you know, if you take a baseline here, it's about -1, you know, up here it's about 2.5, it peaks close to 3. You know, you can see it's gone from -1 to +2. It's gone like 3 degrees higher, whereas temperature risen less than a degree. You know, we're talking about 3, 2, 3, 4 times warming. And if we go up to even the higher Arctic, this is from 67 degrees north. If we go up to 80 degrees north plus the high Arctic, the warming is even greater. So the warming is rocketing upwards. This is Arctic temperature amplification, and it's because of the darkening Arctic, because the sea ice and snow cover in the spring, sea ice is declining, the temperatures are getting warmer and warmer, which feed back, melts more and more ice, makes it darker and darker, and you know, it's a vicious spiral. This is some more data sets. It's adding a couple additional data sets, and just showing, you know, you get the same strong trend upward. I think these two are up in the previous ones. Yeah, these are here. So these two top peaks here are these guys here, and this is some additional data sets. And what this is showing is, this is showing temperature at 925 hexapascals. So if you're at about 900 hexapascals, you're about 1 kilometer up. So this is about 750 meters up in the atmosphere, which is about multiplied by 3.3, I don't know, 2,500 feet or so, half a mile, up into the atmosphere. And what you can see is, this is the warming, and you can see, so the whole air column over the Arctic is increasing, and these are anomalies, 2010 versus 1981, and you can see that at this level up in the atmosphere, there's huge warming pockets over the Arctic. This is again air temperature and sea ice extent. Air temperature going way up, sea ice extent going down, faster than linearly. You know, the curve is bowed. Here's another way of depicting the air temperature in the Arctic. So this is the years across here, beginning of the satellite era to present day, January through to December, and the ranking. So 111. So September 2016 was the hottest in the Arctic. Air temperature rank in the Arctic, 70 degrees north at 925 hexapascal. And you can see hottest, hottest, hottest. This is the second hottest, and so on. So you can see the ranking here, and you can see all the red. This is an interesting way of looking at what's happening. So we're getting more red year-round with a, in this case, the largest. Look at this year, 2016. Okay, a strong El Nino, 2016, 2015. All these record warm months in the Arctic, north of 70 degrees, at less than at 750 meters or so high. Okay, excuse me. Let's move on. Arctic sea ice volume and thickness now. Did we get? Yes. Okay. So don't want to miss anything. Arctic sea ice volume and thickness. Okay. Here's the sea ice volume. Here's the sea ice volume here for different years. Okay, 2007 was minimum extent, the record up until that time, and that was blown away by 2012. Okay, so you can freeze the video to freeze on specific years, but you can see, and this is the ice thickness. You can see the ice getting thinner and thinner and thinner, and the extent decreasing, the area decreasing. Multiply the area by the thickness and you get the volume decreasing, and clearly the ice is rapidly on its way out. This is sea ice volume. I think I showed this this plot was shown earlier, I believe. So this is sort of a recap. All of the red years, record-setting low years for sea ice volume. This is the sea ice volume again, over from year to year. So the 80s, lots of volume, lots of ice. 90s thinner, 2000s less. Here we are, 2010s, and we're bumping near the bottom of the curve. This is the sea ice thickness, the same sort of thing. Here's where we are this year. Okay, the Arctic sea ice extent concentration. Okay, so this is the extent. This is an interesting plot. So this is Arctic sea ice extent. And what we see is this is where we are this year. This is the record 2012 year, the 2007 year, and then last year is the other curve, and then the red curve is this year. Okay, so I'll just let it play through here, and just let it play through. Okay, and what you can see is there's this is extent. So the ice was thicker here, and it was thicker here than it is now. So although the extent is not setting a record, the volume is lower, bumping along, not setting a record, but it's the product of those two that determines it. And the nature of the ice breakup is different. As the ice is thinner and thinner, it's buffeted and blown around, and also as the extent is less, there's less ice being exported out through the Fram Strait. Okay, so this is where we are. This is the extent again. Current versus 2000s, 90s, and 1880s. Here we are with the extent again, the current year. This is the